I'll still go ahead and put the chat on. So if you wanted to throw in the chat, but you can hear me fine. I guess I'm not talking as loudly because, you know, maybe I'll put my glasses on. Oh, never mind. Someone has entered. Did I make you feel guilty? I was getting geared up to talk to an empty classroom. Oh, well, that's okay. Oh, and it wasn't your classroom for very long, Kiana. Morning, Dennis. I'll just let them get their writing utensils out. Does anybody have any questions, quick questions about anything before, while you're getting situated? Let me take a drink of water. I'm thirsty. Yeah, I went to my optometrist for my yearly appointment, and my eye doctor gave me a long speech. She told me I'm getting old and that my vision's going to get worse and worse, and then I'll need bigger and thicker glasses, but it happens to everyone, but my eyes are good. I'm healthy for now. Just like, yeah, I know. It's what you guys have to look forward to when you reach your 40s. But all right, so everyone has his or her stuff out. So repeat the question. Anybody have any questions about anything before we start? So this is where we left off last time. And so, and we're in acids and bases. And there's particular care in the order by which we teach chemistry. I mean, like it's in the order, if I said before, it hasn't changed since 1960. There is a new way to do it. It's called atoms first, but that's just for Chem 161, where you learn all about quantum mechanics first and then go into stoichiometry. But I mean, the order has not changed. And one of the things is that we cover equilibrium before we get to acids and bases, because almost everything to do with acids and bases is directly tied to equilibrium. So, and here's another problem. And as I'm doing these problems, I'm trying to, I shouldn't say try. I don't try, I do. I'm teaching you to see the problem solving as different types of problems and training you to look at this in a kind of a holistic fashion. So look at this problem here. What is the hydroxide ion concentration of a 0.1 molar ammonia solution? So this is an equilibrium problem, and you what's the word? I almost want to say amateur, but that's for love. Apprentice, that's the word, the A word. Apprentice chemist. Start off by thinking about hydrolysis. It's a solution. So you would write the hydrolysis equation. And hydrolysis equation means reaction with water. So this hydrolysis equation, though, we would consider this to be common sense. So you know that ammonia is a base, and you would also either be given to you, you can look up the weak base, the Kb, the base dissociation constant, and know that it's a base. That means it's a proton acceptor, and then it's aqueous solution. So water, and water in this case is the acid. And same idea, write the ice chart, initial change equilibrium. So you have 0.1 molar for ammonia, water is a liquid, not included, 0, 0. So you shift right. So we lose an extent of reaction of ammonia, and we gain extent of reaction for both ammonium and hydroxide. Equilibrium is 0.1 minus x, and x. And then our Kb value is products over reactants, concentrations, all over reactants. Don't include water because it's a liquid. 1.76 times 10 to the minus 5 equals x squared over 0.1 minus x. Use the x as small approximation and then solve for x, right? So x squared is 1.76 times 10 to the minus 6. Or then I guess I can go ahead and it's fun to do notes this way. X is that, so it's going to be, I don't know, 1 point something times 10 to the minus 3. Where am I? Base. So x equals 1.33 times 10 to the minus 3. So also now, if you remember doing all the pH concentration arguments, right? So that means that our hydroxide ion concentration from x is equal to 1.33 times 10 to the minus 3. So the pOH is minus log 1.33 times 10 to the minus 3. And then pH plus pOH equals 14, which implies pH equals 14 minus the pOH, which would be 14. So 14 minus the minus log of 1.33 times 10 to minus 3. So I'm moving this down. Yeah, I'll move this up. So 1 minus log 1.33 times 10 to the minus 3. And then you do that and you get 11.124. And there is your answer. Okay. So recap with this one. And I know I blew through it super fast last class, but I'll explain it more slowly today. So find the pH of a 0.1 molar ammonia solution. So we write the hydrolysis reaction. So ammonia is a base. So proton acceptor, reaction with water. So water is the acid, and it accepts the proton from water to form an extra hydrogen, ammonium, and then one hydrogen away from water, hydroxide. So initially 0.1 molar ammonia, no ammonia, ammonium, or hydroxide. So we shift right. And then we lose an extended reaction for ammonia, gain 1 for each of the products, and then equilibrium, 0.1 minus x, x and x. Kb is products over reactants, ignoring the liquid water. And that means x squared over 0.1 minus x is equal to the Kb. We can do the x a small approximation and then get x equals 1.33 times 10 to the minus 3. So that is also equal to the hydroxide ion concentration. And from that, we can calculate the pH from the hydroxide ion concentration because 14 minus pOH, we need 11.124. So anybody have any questions on this? These ones are a little harder, and it's silly. It's silly why it's harder. And I'm gonna walk towards the screen. So reason why it's harder, and there's in me in my own mind, chemistry the same way. It bugs me that you add the water. That throws me off sometimes, you know, and I have a PhD, right? So I'm like, gosh, this bugs me. You know, it's so much easier with the acids. And then this bugs me, right? Why can't I just do minus log and be done? You know, so those 2 extra steps where you have to have the water in the equilibrium and ignore it, and then the 14 minus the POH to get to the pH. Those are just the, and like, I mean, it's not hard, but it's just like, whenever I do these, my brain, you know, kind of, it's not, I don't know, my heart doesn't skip a beat, but my brain goes, oh man, you know, it's like, I got to take the stairs instead of using the elevator. Shucks, you know, kind of thing. But don't worry, you guys are going to be so well trained at the end of this semester that everything else will seem easy, right? So, and that's one of the reasons why people, I mean, I love chemistry. Chemistry is one of the biggest hated subjects. And I think this is one of the reasons why, because there's just so many little steps that you have to do, and it's all logical, but you have to follow each of the little steps. So, anyone has any questions? Okay. So, and when things are in water, so most of the time, like almost everything that we deal with in acids and bases, although there are acids and bases in other environments, like alcohol, for instance, or alcohols, but when we think acids and bases, we almost always think of water. And later on, maybe today, maybe a week from Monday, we'll talk about acids and bases in other contexts. But pretty much we assume that acids and bases is going to be an aqueous environment. And because of that, there is an exact relationship that when you have an acid and its conjugate base, and the equilibria between the acids and bases, they always equal the kW of water. So, and this is true for every circumstance. And kW, of course, is 10 to the minus 14 at 25 degrees Celsius. So you change the temperature, you change the kW. So, which means if you have a very strong acid, the conjugate base is extremely weak. And if you have a very strong base, stronger than that of water. And the point is that if the base is stronger than water, then the conjugate acid is it's going to be what do we call it? The conjugate acid is extremely strong. So, and I don't know why they have hydroxide as a strong acid. It's not. Oh, it is a strong base. Okay, it's a strong base. Yes. It's a negligible acid. Yes, that's correct. So, oh, I see. It's compared to water. Okay, never mind. So, and from this, this also tells you that cations can be weak acids. So meaning when you look up here for this reaction here with ammonia, so the reverse reaction. So you can have ammonium. So if you have a solution that has ammonium in it, in this direction, I should use a heavier, in the reverse direction, ammonium is an acid. And so from this, the salts then can be weak acids. So salt has 2 definitions in chemistry class. The first definition of salt is it's a metal and a non-metal that's not a oxide or hydroxide. That's one definition. Another definition is the result of an acid-base neutralization reaction. So if you take a strong acid like hydrochloric acid, it's our stomach acid, it's hydrochloric acid, and stomach acid is very sour. So you probably have tasted your own stomach acid at some point in time, and it is very sour and even burning on your throat, right? But it's a very sour flavor. And then there's sodium hydroxide. I've never tasted sodium hydroxide, but I imagine it would taste extremely bitter. So very, very bitter flavor. So we have very sour hydrochloric acid with extremely bitter sodium hydroxide. And when they react together, they form sodium chloride salt. What does sodium chloride salt taste like? Does it taste sour? Does it taste bitter? And the answer is no, it tastes salty, right? So you probably then can tell, okay, salt is something different. So it's not an acid or a base. So salt is the result, or salts in general, are the result of an acid-base neutralization reaction. And salts, so they can have acid-base properties. So although sodium chloride salt, our normal table salt, does not, because, well, I'll talk about that later, it's a strong acid, strong base. But here's a circumstance where you have acids and bases, I'm sorry, you have ions that act as acids. So what about something like aluminum plus 3? Aluminum plus 3 can form a complex, and then it tends to form a complex, and then one of the hydrogens pops off of one of the, I guess you can't see that as well. Let me change colors. Yeah, you can see that, okay. So one of the hydrogens pops off of one of the waters, or one of the waters this is called a ligand attached to there. And that's how it becomes an acid. So we'll talk about a little bit more about this later though. So gearing up to that, we have salts can act as acids and bases. So specifically ions. And students tend to have a really hard time with this. So identify these, each anion as a weak base or pH neutral. So if you remember the strong acids, the strong acids are the halogens except for fluorine, right? Hydrochloric, hydrobromic, hydroiodic, nitric HNO3, perchloric HClO4, and sulfuric, but the first hydrogen for sulfuric. So that means that chloride, bromide, iodide, nitrate, and perchlorate, these ions do not react with water. So that's the anions from a strong acid. So by sulfate or hydrogen sulfate, this is a weak acid. That is in fact an acid. So that one doesn't count. So these anions are neutral. Chloride, bromide, iodide, nitrate, perchlorate. Everything else, all the other anions, they're not neutral. These are the only ones, and they come from strong acids. So identify each anion as a weak base or pH neutral. So the first one, nitrate, this is from nitric acid. This is neutral. So then nitrite, so it's HNO3 minus, it's not HNO2 minus. HNO2 nitrous acid is a weak acid. So this is a weak base. And then acetate is the next one. Well, it doesn't matter. Just look at what the name is. That is acetate, but look at the other ones. It's not chloride, bromide, iodide, nitrate, or perchlorate. Therefore, it's a weak base. So this is where you can speak in absolutes. I've been watching Star Wars lately. So they say the Sith are the only ones that speak in absolutes. And I can speak in absolutes too. I guess that makes me a Sith or something. So these are the absolutes. So if it's not chloride, bromide, iodide, nitrate, or perchlorate, it's going to be a weak base in water, in an aqueous solution. So questions with this one? So let's do a problem with this. Wait a second. Why did that go away? How did I go to settings by dropping my Apple Pencil? All right, so pH of a 0.1 molar sodium formate solution. So this is, again, you write out the hydrolysis reaction, formate ion plus water in equilibrium with formic acid and hydroxide. So initially, you start off with 0.1 molar formate. Water is a liquid, you don't include it. No, none of that. No formic acid, no hydroxide. Which way do you shift? You shift right. equilibrium 0.1 minus x, x, x. And you can look up the Ka for formic acid, and it's 1.8 times 10 to the minus 4. So how do you get the Kb for the formate? I'm sorry, the formic acid Ka is 1.8 times 10 to the minus 4. What about the Kb for formate? Well, if you remember in the previous slide, the Ka times the Kb equals Kw. So that's where this comes into play. And then your Kb for the formate anion is going to be 5.6 times 10 to the minus 11. So that means Kb is going to be 5.6 times 10 to the minus 11 equals, it looks like H. It's going to be formic acid, hydroxide, all over CHO2 equals x squared over 0.1 minus x. Jeez. I need to recalibrate my Apple Pencil. Well, you can use the x is small approximation. So that means x is going to be the square root of 5.6 times 10 to the minus 12. So that's going to be what? 2 point something times 10 to the minus 6. Equals 2.4 times 10 to the minus 6. And what does it want? It's a pH. It's the same idea. So we know the hydroxide ion concentration, because it's X. X is also equal to the hydroxide ion concentration. It's going to be 2.4 times 10 to the minus 6. pH is 14 minus the POH. 14 minus log 2.4 times 10 to the minus 6 equals 8.38. Okay, so what? Why do we care? Well, this is weird. We take sodium hydroxide and we react it with formic acid, and we thought, okay, we have a base and acid. It reacts and it forms a salt, sodium formate, in water. That's what acid bases do. They form salts in water. So, but it turns out then further down the line, sodium formate. Now this as a salt, you dunk it into water, you're going to have an alkaline solution. So this is a way you can calculate then the degree of the alkalinity of the solution. So how does this work? Questions? Or I guess I didn't do a recap. Okay, recap for this one. And you can see these problems are starting to look similar, right? So this is really the same problem as the ammonia problem. The only difference is that you're given an anion, and then you have to do this extra step where you have to calculate the Kb. So it's the same thing as the ammonia problem, but now you have the extra step where you have to calculate the Kb from the Ka. And same logic, almost same numbers, actually, it's the exact same procedure. So write the equilibrium expression, do the discount x is small approximation, and then take the hydroxide ion concentration, 14 minus the POH, and get the pH. You can see this is, if you remember ammonia's pH was 11 something. This one is 8. So it's an alkaline solution, but it's not that alkaline, right? So neutral 7, right? So this is not that alkaline. So you probably, I wonder if you'd even taste it. If it even taste bitter. Any questions? All right, so I guess I'm probably showing my age. I already told you about my optometrist yelling at me, not yelling at me, giving me a speech. I remember when I was a kid, we had the WWF, the World Wrestling Federation, and they had like the people like like Macho Man, Randy Savage, and Andre the Giant, and then they would fight and they would wrestle. But I mean, the thing is, you always knew who was going to win. It wasn't like a surprise who was going to fight, you know, like especially with Andre the Giant, all of those guys, Andre the Giant, or sometimes it was Macho Man, Hulk Hogan. I mean, like there was someone that was always going to win. Anyways, I always, when I was learning this, I went back to my WWF days, and I'm like, "Are you ready to rumble?" And then the asses and bases would fight, and then there was always one that was stronger. The stronger one wins. So, and the way I always kind of thought of it was, okay, so if you have a strong ass and a strong base, strong ass and strong base, they fight, and they like completely destroy each other, and that means it's a neutral salt. So let's say you have a really strong base and a weak acid, and the strong base flattens the weak acid. And now there's whatever's left over, because the base was so strong that now the solution is basic. And then you have the other thing. So let's say you have a really strong acid and a weak base, and a strong acid smacks down and beats up that weak base. And it's, what happens though is that this leftover pile of rubble is now slightly acidic. So if you have two strong things that are equally matched, it's neutral. If the base is stronger, the base is strong, it's got a weak base. If you have a strong acid, goes to a weak acid. If you have two tiny weak acid, weak base, and they fight, you don't know. You have to look at the equilibrium. So whichever one is bigger. If the Ka is bigger, then it's going to be acidic. If the Kb is bigger, it's going to be basic alkaline. So the real reason, that's my mind, that's the way my mind interprets it. But the real reason is, so if you have a strong acid, strong base, and they fight, you have the anions, they don't react. They don't react with water, therefore it's neutral. If you have a strong base and a weak acid, okay, they neutralize. The counter ion for the strong base is not going to react with water, but the counter ion for the weak acid will react with water, and weak acid anions reacting with water, the hydrolysis reaction, rip hydrogen off of water and form hydroxide. So that's the reason why they form strong bases. It's not because the base is so powerful it beats it down. It's because of the reaction with water. Same idea with strong acid and weak base. You have a strong acid and then it reacts to the weak base. So the counter ion for the strong acid doesn't react with water. The counter ion to the weak base, though, does react with water, and it reacts as a proton donor. And then because of that, the solution is slightly acidic. And then same idea for the weak acid, weak base, but it just depends on the equilibrium. We just don't, depends on the size of the equilibrium. So does that make sense? I mean, like that's the way, I mean, I guess a computer would understand it better, you know, looking at the equilibrium values. But just for me, that's the way I digested it. It was just two things fighting like in a WWF wrestling match. So, but okay. Determine whether or not the solution is acidic, basic, or neutral. So strontium chloride. And this is where I'm going to contradict myself, as chemistry often does. So chemistry contradicts itself. So the strong bases are the alkali metals and some of the alkaline earths, but for salts being alkaline or basic, all alkaline earth salts act like strong bases. So the only bases that are weak bases are the ones that are not from alkali metals or alkaline earths. So alkali metals being sodium, lithium, or lithium, sodium, potassium, rubidium, cesium. Alkaline earths being beryllium, magnesium, calcium, strontium, barium, radon. So just down the periodic table. So we have our fight. We have strontium chloride. So what is fighting? We're going to have strontium hydroxide which is a strong base, and hydrochloric acid, which is a strong acid. So we have a strong acid and strong base. They're fighting each other. And what happens? I'll use green. This forms a neutral solution. So the strong acid and the strong base, they react and they form a neutral solution. So now we go to aluminum tribromide. And in our mind, we have, I shouldn't use that blue. We're going to have aluminum hydroxide and hydrobromic acid. So aluminum hydroxide, is that a weak or is that a strong base or a weak base? Well, it's not an alkali or an alkaline earth, therefore it's a weak base. Hydrobromic acid, a strong acid. These ones fight, the strong acid wins. So this solution has an acidic salt. So aluminum tribromide is an acidic salt. Why is aluminum an acidic salt? And if you remember, I had the image, I actually had aluminum. It forms a complex and with water, it's called, in fact, it's called a ligand. I guess we don't talk about it this semester, but it forms an octahedral complex where there's aluminum in the center, and then you have 6 waters around it, and then one of the hydrogens pops up of water. So aluminum tribromide in water is an acidic solution. And again, you can remember that it depends. You can look at it from the real reason, or you can use my fighter logic. You have strong acid, weak base. You got some leftover acid in that fight. So next one, that is methylammonium nitrate. So you might notice that nitrate, that's from HNO3, nitric acid, and then you have methyl ammonia. It's kind of like ammonia. So what is that going to be? This is going to be a weak base, CH3NH2. This is a weak base, and you have a weak base and a strong acid. Therefore, that's going to be an acidic salt. And then the next one, sodium formate. We just had a problem with this. You know it's alkaline. And why is that? I'll use blue. We have sodium hydroxide and we have formic acid. So we have a strong base and a weak acid. This means that it's going to be a basic salt. So, and we just did a problem with this showing you how the equilibrium works. So strong base, weak acid, leftover pile of rubble is a weak base. And then last one here, ammonium fluoride. We have ammonia, which is a weak base, and you have hydrofluoric acid, which is a weak acid. And what is this? What is the answer to this? We don't know. We don't know. We have to look at the relative size of the Ka and the Kb. I think it's probably going to be acidic. Let's see what it is. Yeah. So it turns out that the Ka for hydrofluoric acid is bigger. So I won't ask this question, at least on a test. I won't ask this question on a test. So I don't think I answer it. I don't think I ask it as a homework question either. I mean, as far as a weak acid, weak base and determining the value, certainly not. But if you look up the values, the Ka is greater than the Kb, therefore it's going to be acidic. That's going to be a greater than. So the Ka is bigger than Kb, therefore it's acid. All right, so recap for this one. Strontium chloride, strong base, strong acid. neutral salt. Aluminum tribromide, weak base, strong acid, acid salt. Methyl ammonium nitrate, weak base, strong acid, acid salt. Sodium formate, strong base, weak acid, basic salt. Ammonium fluoride, weak base, weak acid. We don't know. We don't know what the result is. We have to look it up, and it turns out it's an acid. Questions with this? Okay. How about potassium acetate? That's the delicious stuff that they put on salt and vinegar potato chips. Sometimes sodium acetate. So what do you think? Do you think this is an acid salt? Do you think it's a neutral salt? Or do you think it's a basic salt? No one's playing. Okay. Potassium. What base do we get from potassium? We get potassium hydroxide. Is it a strong base or a weak base? It's a strong base. Right, so periodic table, here's potassium. So potassium is an alkali. The word alkali means basic, alkaline. So potassium hydroxide is a strong base. So strong base. And what about formate? So where do we, well, is formate, is that the counter ion of a strong acid? So that means, Pete shaking your head, no, that means it's a weak acid. So you have a strong base plus a weak acid. And what happens when we have a strong base plus a weak acid? Yep. Becomes basic and or alkaline. So questions with that? Which way do you like better, the equilibrium, or do you like the acids and bases fighting? I like the acids bases fighting. All right, well, whichever way works the best. Okay. So once you've gotten used to all these things I've been talking about, you find out I'm gonna throw another thing at you. And the new thing I'm gonna throw at you is polyprotic acids. So we've only dealt with monoprotic acids. We talked about like hydroxide, well, it's not hydroxy, it's going to be maybe hydroxides of other metals, but I mean, there's not really that much of an equilibrium with them, at least not yet. We have the strong bases because they completely disassociate. But now we have acids, and there are acids that have more than one proton. They're called polyprotic. The nice thing about polyprotic acids are you only have to worry about the first hydrogen because the rest of them are negligible with the exception of sulfuric. So sulfuric acid is the only one you have to worry about, and sulfuric acid calculations are just a royal pain in the side. So sulfuric acid is the only one you have to worry about, but the rest of them, here are some other ones. Oxalic acid. So oxalic acid, that's what you find in taro, right? That's the reason why you have to cook taro, because the oxalic acid crystals will poke you on the way down. And sulfurous acid, so just like sulfuric, but one less oxygen. Phosphoric acid, citric acid, right? You can see citric acid's got 3 protons. Whew. Ascorbic acid, so anti-scurvy acid. Vitamin C, there's another one, and carbonic acid has 2. So, but when you do these calculations, and you can do the second part if you want, but what you always find out is that the subsequent values, and you can see there's different values. There's Ka1, Ka2, Ka3. There's even quadraprotic acid. So EDTA, ethylene diamine tetraacetic acid. That's a quadra proton, whatever, tetraprotic acid. Sorry, not quad, tetraprotic acid. So there's even 4. So, and there's equilibrium values for each subsequent hydrogen, proton. And when you do these calculations, like I said, honestly, you don't have to worry about the first one, with the exception of sulfuric. So sulfuric is the one you have to worry about. And I will, do I have the, okay, here's the sulfuric one. So I got to do the math on this one. This is, got to pay attention. Okay, so sulfuric, so let's do the pH of a 0.01, so a centimolar sulfuric acid solution. And there's 2 Ka values, and the first one is strong, the second one is weak. So it's a strong acid, therefore it completely disassociates. So you notice this first one, there is an arrow. There is no going back. So first step is an arrow. The second step, though, is an equilibrium. So sulfuric acid, if you throw this in water, it's as if you did 2 things. You threw a sulfuric acid in water, and now it breaks apart into hydrogen ion and bisulfate. So that's step 1. And now step 2, bisulfate is in equilibrium with hydrogen ion and sulfates. So then we do the initial change equilibrium. So the first step, it's easy. It completely goes away. The sulfuric acid, after the first step, all the sulfuric acid is gone. And it's all turned into hydrogen ion and bisulfate. Now the second step, same idea, but the difference is you have the common ion effect. So you have 2 acids mixtures, but you have initially 0.01 molar of hydrogen ion. So it shifts it a little bit. And unfortunately, we can't use the X of small approximation. So same idea. Let me do blue. I like blue. So our Ka value would be Ka2 is going to be 0. Well, it's going to be hydrogen ion, SO4 minus 2, sulfate, bisulfate. This equals 0.012 equals 0.01 plus x over 0.01 minus x. So you see that. Now the next step is you have to get it down to the ax squared plus bx equals c. So you multiply both sides by 0.01 minus x, so you get 0.0012 minus 0.012x equals 0.01x plus x squared. So I'm just multiplying the x's through, and now I have to add to both sides. Am I doing this right? So then you are going to get x squared plus 0.022x minus 0.0012 equals 0. Now let me look at my book and make sure that I'm I missed a 0. It's like something looked wrong. I'm missing a 0 here. Right, because that's 0.01, so there's another 0. Yes, 3 zeros, 1, 2. Okay. So now we do the quadratic equation. and we have x equals negative b minus 0.022 plus or minus the square root of b squared, 0.022 squared minus 4 times a is 1, c is 0.00012, all over 2a. Let's put 2. Okay. So let's do some logic here. And I know the quadratic equation says plus or minus, but let's look about what this means. So we have a negative, so this numerator, this number, it needs to be positive. So we have the x, among other things, is going to be the sulfate concentration. And there is no such thing as a negative concentration. And if you look at the math here, right, so you have, this is a negative number. So when you're doing the math here, we have negative 0.022, and plus or minus, you're going to have the square root of the same number squared, and then the minus is going to be a positive. So this value, this square root value, this is slightly larger than 0.022. So if you do plus, you're going to get a small positive number. If you do minus, you're going to get a bigger negative number. So you can go through, if you don't want to do the logic, you can go through and do both, but it's the plus. The plus root is the one that's the proper one, not the negative one. So you can just go ahead and throw out the negative one. And if you throw out the negative one, you get x equals 0.0045. So, okay. So now we have x equals 0.0045, and we want to know what the acid concentration is for the pH. It's going to be 0.01 because sorry. Why is this? There we go. I must have spit on the screen or something like that. There we go. How did I spit on the screen? I'm wearing a mask. I'm not sweating. Anyways, so the acid concentration is 0.01 plus x. So 0.01 plus 0.0045. So it's going to be 0.0145. And now the pH is equal to the minus log of the hydrogen ion concentration, 0.0145. And then to 2 sig figs, it's going to be 1.84. So, all right. And if it makes you feel better, you only have to do this for sulfuric. So unless you've got some weird controls that you need to go further for calculating out the equilibrium. But at this day and age, I honestly cannot think of an application, and I can't think of a machine that has the ability to discern the pH levels of the subsequent values of weak acids. So sulfuric acid is the only one that you have to worry about this with. So sulfuric acid is as if you're mixing two acids, if you're mixing a strong acid and a weak acid. So you throw sulfuric acid in water, first step, dissociates completely. First step, boom, comes apart. Second step, equilibrium. So you set up the equilibrium and you set it up to include that common ion, to include the hydrogen as a common ion. And the difference is you have to have then that 0.01 initial step, and you shift right. You still know you shift right because you have a 0 in the sulfate. So it's easy to find which way to shift. When there's a 0, you shift right, and then you set up the equilibrium expression. You FOIL it down to ax squared plus bx plus c. Then you throw in the quadratic equation, and then you can calculate both roots if you want. I like to use logic as much as I can because I hate throwing numbers in the calculator. That's just myself. However you want to do it is fine with me. If you must know, the second root is negative 0.027 as I'm looking at the book. But it's easier just, I like to just logic my way out of it. Because if I'm using logic, I also know that I'm doing the problem correctly as I'm going through. So, and then you throw that back in the equilibrium and then calculate the pH as you normally would. So, questions with that one? That one's a hard one. That one's a hard one. If you notice, I was trying to be extra careful, and I knew there was something wrong actually. I was like, I'm doing something wrong, and I like, this is 0. So I was forecasting ahead. I'm like, I missed something here. So so pay attention as much as you can. And like I said, chemistry is just so many little steps. You miss one, it's bam, you got the wrong answer. You're like, where did I find it wrong? It's like a detective looking to figure out where your mistake was. So, okay. All right, and we're coming to the end of our talk with acids and bases. And so it's almost like a philosophical thing. Now it's time for, it's like, why do acids, why do acids act like acids? What is about acids that make them act like acids? And if you go on, you start talking about, and you get into organic chemistry, they talk about this, something about acidic hydrogens. So if you go on and you start studying organic chemistry, so if you have something like, so do I talk about carbon? Okay. So how many of you want to take organic chemistry out of curiosity? You guys want to take organic, or you say you are? Okay. Are you Dennis, or you don't know? What's your major? Okay. Maybe, maybe not. Depends on. So actually, probably if you're going on engineering, probably not. So, but I'm also looking at many of you are taking organic chemistry. So the hydrogens attached to carbon and methane, these are not considered acidic hydrogens. But then if you have methanol, that hydrogen there is considered an acidic hydrogen because it's weak. What happens is the oxygen, so there's an electron cloud around hydrogen, there's an electron cloud around oxygen, but the oxygen is more electronegative and it draws electron density towards itself. And then because of that, this bond here becomes weak. It's easy to break that oxygen hydrogen bond. So then if you look at the different oxyacids here, so this is the chlorine oxyacids, and notice if you have hypochlorous acid, so this is perchloric acid, this is chloric acid, this is chlorous acid, and this is hypochlorous acid. So per means extra hydrogen, hypo means one less. So, and when it comes to the hydrogen bond, hydrogen, well, bonding, not necessarily hydrogen bond, but the bonding with the hydrogens, you have this hydrogen here, the electrons are being drawn towards the two electronegative atoms, and it makes this bond very weak. And if you have another oxygen, it draws it even more. If you have two oxygens, it draws it even more. And you can see what is happening when you're adding more and more oxygens. The Ka value is going up. That's not a very big number. This is getting to be a fairly big number. One is reasonably sized. That's a pretty strong acid. I wouldn't want to splash that in my eyes. Now you get to 4 oxygens. Now this is a strong acid. So the electrons, so hydrogen has an electron cloud, but as time goes on, well, I guess time, it's actually independent of this. The density around hydrogen and the electron density is then drawn away from the hydrogen. And remember, electrons are kind of like these fuzzy clouds. So the electron density gets drawn away to those really electronegative atoms. I try to draw one around chlorine, but smaller, because the chlorine is still electronegative, not as electronegative as oxygen. And it makes this bond here very weak. If that's a really weak bond, that means it's really easy to break. And it's also really easy for this molecule to donate positive charge to something. And that's what acids do, is they donate positive charge. Bases donate negative charge. So, or you can look at the other way around. An acid is an electron vacuum cleaner. And a base is an electron source. So that's probably a better, me personally, I tend to think of it more as the Bronsted-Lowry, proton donor, proton acceptor. So either way works, donating positive charge or accepting negative charge. They both mean the same thing, and vice versa. But it comes from the fact that acids have a really easy way of gobbling up electrons to donate a positive charge to something else. And there are stronger bases. So like in other solutions, so also in organic chemistry, you can create something called like an ethoxy or methoxy ion solution. So if you take sodium metal or potassium metal and you throw it into an alcohol like methanol or ethanol, if you throw sodium metal into methanol, you get a methoxy ion solution. If you throw sodium or potassium into ethanol, you get a ethoxy ion. So those ions are stronger than hydroxide. So there are certain reactions. I remember there was this, I did a reaction like this, and I don't know if they'll let you do this anymore because of safety purposes. So there's something called a sodium fusion reaction. I had a chlorinated hydrocarbon, and we were doing experiments with a chlorinated hydrocarbon. And so it was a liquid. It was a liquid chlorinated hydrocarbon. And then I took a piece of sodium. It wasn't just me. It was this is an organic chemistry lab. And you had a piece of sodium into a small test tube. And you would heat the test tube in a Bunsen burner. And you got the test tube really hot. It was glowing red. And then you would take it immediately from the flame and stick it into the liquid, liquid alkylated hydrocarbon. And the thermal shock from putting the hot glass into the liquid would shatter the bottom of the test tube. And then the liquid sodium would go in, and then there was a reaction. And then the idea was that the sodium would rip off the chlorines from the organic molecule, the carbon-containing molecule. And then that's called a sodium fusion lab. And that was a lot of fun, but it was kind of, at the same time, it was kind of scary because, you're shattering glass with liquid sodium, which would really hurt, of course. But like I said, I don't know if they'll let you do this today. This was back in the 90s. So, but okay, so conceptual wise, which of the protons shown in red is more acidic? So we have formic acid on the left on A, and we have methanol on the right. These are both considered acidic hydrogens. But this one is even more. So the same idea. You have this extra oxygen here. You have two oxygens, and then this is the oxygens are the electron vacuum cleaners. They're drawing the electron density away from the hydrogen, making this bond weak. So for this bond is weak too. So if you throw methanol, if you throw sodium metal into methanol, sodium metal will grab that hydrogen, and you will form, if you throw this into sodium into that, because it's a liquid, you'll form hydrogen gas plus sodium methoxylate. So and this is beyond the scope of this class though. So I mean this is an example of an acid-base reaction outside of an aqueous environment. So, and you even have this, I even called this formic acid, that's another hint, because the name of this thing is an acid, which one's the acid? Is it the acid or the thing that's not named acid? So formic acid, and this group here, this is known as a carboxylic acid group. Anything attached to carbon, double bond, O, OH. That's called a carbonic acid group. So you have many things that have carbonic acids. So fats, they're also known as fatty acids. Fats have that at the end of them. So acetic acid, this is formic acid here. Acetic acid is another carbon. This is acetic acid vinegar. If you have another carbon, that's known as propionic acid. So propionic acid smells horrible. That's one thing. If you study organic chemistry, it's a very stinky. If you go into an organic chemistry lab, it smells. And so I don't mind the smell of vinegar. I think it's kind of pleasant actually. But propionic acid, ugh, bad stuff. And butyric acid, oh, it's even worse. That's like stinky feet. So, okay. And then I kind of hinted, that acids and bases, that you can think of an acid. So, right, so an acid, it donates, so positive charge. Acids donate positive charges, bases, they donate negative charge. And we explicitly say that it's the proton, the +1, that's moving. What's really going on, and like for hydrochloric acid, what's really going on, like you have the electrons here on the water, and the electrons are not even two dots, it's a fuzzy cloud. So there's this fuzzy cloud here, and it moves towards the bond, this bond between hydrogen and chlorine, and then the electron density goes into the anti-bonding orbital, and then when the bond order becomes 0, enough electron density is added to the bond, and it's in for electrons transferring from one molecule to the other, it's going to be a full electron. So electrons do have uncertainty in their position and momentum, but there's not enough of it that they can be in two different molecules at the same time. They're not that uncertain. So they are uncertain, but they're not that uncertain. I know it's kind of weird, when we talk about this in terms of quantum mechanics, and but there is uncertainty where it flows, but once it goes a certain distance, it's kind of all or nothing. It just pops off. So the electrons, there can be uncertainty within the molecule of water, but if you're talking between hydrochloric acid and water, there can be uncertainty as the electron is transferring, but at a certain point, the electron picks a side, and the electron, in this case, 2 electrons transfer to the anti-bonding orbital. And when that happens, you then get chloride, anion, and I know I'm drawing it like a Lewis structure, and you're left with just a proton hydrogen. And then the proton hydrogen then goes and it moves over to water and forms a hydronium ion. So, and furthermore, you can get, and this is called Lewis acids and bases. So these are Lewis. So if you remember, there's 3 definitions for acids and bases. There's Arrhenius. Arrhenius says, if you throw acid into water and it forms hydronium or hydrogen ion, it's an acid. If you throw a base into water and forms hydroxide or well, hydroxide, it's a base. Very simple definition. Then you have the Bronsted-Lowry, where you say, well, water, or so you have an acid is a proton donor, base is a proton acceptor, and that works really well. There's a model. And then you have Lewis theory that says bases are electron donors and acids are electron acceptors. And Lewis theory fits the other two perfectly because Lewis theory explains how the proton goes from the acid to the base, because the electrons go from the base and populate the anti-bonding orbitals, and then as the electrons transfer, then the hydrogen is released from the acid, and then it attaches to the base. So that's the best one. But there are certain reactions that happen that are not aqueous, that water is not involved, and you can get acid-base reactions. Although you can also describe, like here, formation of carbonic acid. I mean, you could describe carbon dioxide as an Arrhenius acid because when you throw it in water, it forms an acid. But the process, how it works, is explained through Lewis acid and base theory. So the water is a base. It donates electron density to the carbon, and then it forms, then the electrons shift and you form carbonic acid. And there are other things that go on. So if you look at this reaction here, so ammonia can react with aluminum trichloride, and it can form this new molecule. So it wouldn't be ammonium, it would be this, I don't know how I would name this molecule, but in a way, ammonia is donating electron density to aluminum trichloride. And you can see then that this ammonia would be a base, and then aluminum trichloride would be an acid. And when I was a student of studying this, I had a hard time with it. It's just like, well, geez, whenever you have an electron transfer reaction, it's an acid-base reaction. So although we don't always consider them to be acid-base reactions, that's kind of the way it is. So acids and bases, it depends on how big you give your box, what an acid and base is, but then you also have to bring it back down to how they act. So, and I know it's, I'm kind of exploding it to say everything is an acid-base, but at least when you transfer electrons, it's an acid-base reaction. But there are certain consequences of things that act like acids and bases. And one of them is, most importantly for us, is biological. So when things interact with a biological surface. So I told you one of the reasons that bases, when you touch them, if you get bases on your hand, they feel slippery. So like if I ever work with bleach and then when I'm done, I always, is my finger slippery? And the answer is no. No big deal. If they say, oh yeah, slippery, and I run it under running water until it no longer feels slippery. So because base burns take time. Why does that work? Why does bases make things feel slippery? One of them is because bases add negative charge, and also biological surfaces, they also tend to be negatively charged. So cell membranes, for instance, they're phospholipid bilayers. So right, remember that phospholipid, we talked about that with micelles. You have a phosphate group and a hydrocarbon. So the phosphate group, that means it's negative along the phosphate group, and then you have the hydrocarbon tail. So that means that when things approach a cell membrane, cell membranes on the outside is all negatively charged. Of course, there's positive charges hanging around, sodium, potassium, but the surface of a cell is negatively charged. So when you have bases and you add more electron density to things, what happens to biological surfaces is they get bigger. So if you were to add a base, if you put a cell and you add base around the cell, what happens to the cell is it expands because you're adding negative charge to an area that's already negatively charged. And that happens for hair. So if you, I don't have very much hair, but when you do hair chemistry, say you want to dye your hair, there's a couple of ways you can do it, but the first step is always you put something alkaline into your hair. So usually lye, sodium hydroxide, or bleach. Bleach will go directly. And what happens when you throw bases like sodium hydroxide in your hair, the hair follicle gets bigger, and then you can do chemistry inside the hair. So bleach, there's already natural pigments, melanin and pheomelanin. It's kind of the brown, the red color, kind of, sort of. And then you, if you have bleach, that's already a base, exposes it, then you oxidize the dyes, and then you bleach your hair. So, or you can put bleach in and you can expand the hair follicles, and you can put a dye inside the hair. So that's what you're doing when you put hair dye in. Say I want my hair to be red, so I put sodium hydroxide lye, my hair follicles get big, and then I put in red dye in the solution, and then I wash my hair, and then the hair follicles shrink back down because there's no longer the negative environment from the base, and now I have the red dye trapped in my hair follicle, and like inside the hair, so my hair looks red. Let's say I get stung by a jellyfish. So what do I need to do? Well, the stinger cells, they're biologically active. I'm being stung. I want to shrink the cells. So if I were to put base on a jellyfish sting, I would probably make it hurt worse. What you do is you add acid. So remember, biological surface is negative charge. What happens when you add positive charge to a negative surface? It shrinks. So jellyfish stings, you add vinegar. People say use urine, but urine's pH is like 6 and vinegar's pH is 3. So it'll work, but vinegar works 1,000 times better. Or you can use lime juice and it'll work 10,000 times better because it's a pH of 2. And then when you do that, the stinger cells shrink quite a bit, and then the stinging can stop. I've noticed that a lot. Citrus is my go-to when I get stung by a jellyfish. So you can see that. So biological surfaces, positive charge makes things shrink, and that's how you treat jellyfish stings. And then negative charge things blow up, and that's how you dye your hair. Do hair chemistry that way. So that's kind of the so what's with that. But of course, that's just one of the many, many applications for acids and bases because we use them all the time. And that's my shut up alarm. So I will shut up and I will stop recording. Anybody have any quick questions? Yes, please, Dennis.